Okay, let's dive into this. Imagine you're trying to map, I don't know, a huge, sprawling city,
Hmm.
but you're stuck inside it, maybe in a car with slightly foggy windows.
Yeah.
You only ever see little bits and pieces as you drive around. How do you possibly build a complete picture? Figure out its layout, its history, even the unseen things holding it together, like uh, gravity.
Yeah, that's actually a pretty good analogy for studying our own galaxy, the Milky Way. It's a complex problem for sure.
Right? Because we can't just like step outside and take a panoramic photo.
Exactly. We're embedded within it. So we have to piece together all the information we can get from, well, billions of individual stars that we can observe, plus gas, dust, and the subtle signs of dark matter, too.
And one of the really powerful tools scientists use for this to make sense of this just immense amount of data is building models, specifically something called stellar population synthesis models.
Mm.
Today, we're doing a deep dive into one particular model that's been, well, really central to understanding our galaxy, especially with the European Space Agency's Gaia mission. That's the Besançon Galaxy model, or BGM.
Yeah, the BGM. It was absolutely crucial in preparing for Gaia. And now actually comparing the model to Gaia's incredibly precise data, well, it's giving us totally unprecedented insights into the Milky Way's structure, its history, even its gravitational potential.
So our mission today, for you listening, is to unpack what these population synthesis models actually are, how this Besançon model was constructed, why it was so vital for Gaia's success, and maybe most fascinatingly, what we're learning right now by comparing it to Gaia's measurements. We're drawing on sources that detail the model's background, its structure, and these recent applications.
Sounds good. Let's get started.
All right, so let's start with the big picture. What is population synthesis modeling? What's the basic idea?
Okay. So, at its core, it's really about explaining the properties we observe from a collection of stars. Could be a whole distant galaxy, could be just a patch of our own Milky Way based on the physics of how stars are born and how they, evolve over cosmic time.
Right. So for a galaxy really far away, we can't see individual stars. We just see this like combined smudge of light.
Exactly. You get the integrated light, maybe spread out into a spectrum.
Right.
For those distant galaxies, the models usually start with some assumptions, things like the initial mass function, that's the distribution of masses stars tend to be born with, and maybe the star formation rate, how quickly stars formed over that galaxy's lifetime.
Okay.
Then, using what we know about stellar evolution, the model calculates what the combined light, the spectrum of all those stars should look like.
And then you just compare that prediction to what your telescope actually sees.
Precisely. And you adjust the model's assumptions, the IMF, the star formation history, maybe the age of the stars, until the model's output matches the real observations. This approach, well, it goes way back. People were successfully using models like this in the 70s and 80s to understand galaxy colors and spectra.
Okay, so that's for distant galaxies, matching the overall light.
Okay.
But for our galaxy, the Milky Way, we have this different situation. We can see individual stars, tons of them. So how does the modeling work when you're inside the system?
Right, it's a different ballgame. For the Milky Way, instead of matching integrated light, we compare the models to star counts. So we simulate stars based on our best guesses about the galaxy's structure, the different components like the disk and halo, and how the stars within them formed and evolved.
So you build a fake galaxy in the computer.
Sort of, yeah. For each simulated star, we calculate its expected properties, how bright it would look, its color, its position on the sky, even its motion.
And then you compare that simulated star catalog to what actual telescopes and surveys are finding.
Exactly. You look at a specific patch of sky and ask, does the model predict the right number of red stars, blue stars, bright stars, faint stars, compared to what we actually observe there? By seeing where the model matches and where it doesn't, you can refine those initial assumptions about galactic structure, star formation history, kinematics.
Kinematics?
Yeah.
How the stars are moving?
Yeah, their speeds and directions. This whole star count modeling approach for the Milky Way really got going back in the early 1980s.
What kicked it off then?
It was largely driven by needing predictions for upcoming missions, especially the Hubble Space Telescope. People needed to know what Hubble was likely to see in different directions.
Planning observations.
Right. Early influential models, like the Baikal-Sonera models, were used for exactly that, but also for tackling bigger questions, like understanding the structure of the galaxy's halo, or even figuring out how many background quasars might be visible through the foreground stars. And this technique is still very much alive. Similar models are being developed right now to prepare for the Vericy-Rubin Observatory, which will be surveying the sky incredibly deeply.
So it's a method that's constantly being updated as our observational tools get better. But it sounds like the Besançon model isn't the only game in town.
Oh, definitely not. While we're focusing on the BGM today, it's useful to know there are other sophisticated models out there. They might use slightly different techniques or focus on different aspects of the galaxy.
Can you give us a couple of quick examples?
Sure, there's a model called TRILEGAL. It's based more on theoretical luminosity functions, basically, how intrinsically bright different types of stars are expected to be. It models the galaxy with five main components: thin disk, thick disk, halo, bulge, and also an explicit layer for dust extinction. And it was calibrated against data from missions like Hipparcos.
Hipparcos, Gaia's predecessor in a way.
In a way, yes. Then there's another model developed by Just and Jaures. This one used dynamics, how stars move locally, near the sun, as a key constraint. It focused particularly on main sequence stars in the disk nearby, and it gave insights into the local star formation rate and the IMF. That one's been compared against various surveys, including early Gaia data releases combined with others like RAVE and Apogee.
So that one's like a more zoomed-in local view.
Kind of, yeah. And another one to mention is GalMod. That's another star count model, but it includes more detailed features like an asymmetric bar at the galaxy's center and representations of spiral arms along with the dust associated with them.
Okay, so there's this whole ecosystem of models tackling the Milky Way. Let's bring it back to our main focus, the Besançon Galaxy model. What are its key features? How is it structured?
So the BGM, in its, let's say, classic form, represents the galaxy as an axisymmetric approximation.
Axisymmetric, meaning it assumes the galaxy is basically symmetrical if you spin it around its center.
Like a frisbee. Roughly, yes. It doesn't explicitly include things like spiral arms or a lopsided bar in that basic version. It models the four main large-scale stellar populations we generally talk about: the thin disk, the thick disk, the stellar halo, and the central bulge.
The big building block.
Right. And crucially, within the model, each of those populations gets its own recipe, its own assumed star formation history, its own specific set of rules for how its stars evolve based on stellar physics models.
And what were the main goals when it was being developed?
The core objectives were twofold, really. First, to simulate realistic star counts, numbers, colors, magnitudes that could be directly compared with actual observations. And second, maybe more importantly, to use those comparisons to test our underlying assumptions about how the galaxy works. Things like the star formation rate over time, the initial mass function, and the details of stellar evolution itself.
So it wasn't just about describing the galaxy as we see it, but actually testing the physics and history we think produced it.
Precisely. It's a tool for testing hypotheses.
Now, you said earlier the BGM was absolutely central to preparing for Gaia. That seems counterintuitive. How does a model help before the mission even launches?
Yeah, it was fundamental, really. From the very early days of Gaia planning, back in the 1990s, the BGM was a key input for the Gaia simulation working group.
What were they simulating exactly, those mission?
Pretty much. They needed to simulate the entire process: how Gaia would scan the sky, what it would see, how the instruments would respond, and how the data would flow. A critical piece of the simulation was something called the universe model. Its job was to generate a realistic, simulated catalog of everything Gaia might see down to its faintness limit.
Okay.
And for the stars in that simulated universe, which were the vast majority of objects, billions of them, including binary systems, the underlying galactic structure, the distribution, the types of stars, all that was based on the Besançon Galaxy model.
So Gaia's planners were essentially flying the virtual Gaia satellite through a simulated Milky Way powered by the BGM.
That's a really good way to put it, yeah. The universe model spat out all the details for each simulated star that Gaia would eventually measure: its position, distance, brightness, color, its motion, even realistic estimates for the measurement errors Gaia's instruments would likely produce.
Okay, I get what they did, but why was this simulation using the BGM so absolutely essential before launch?
Oh. It was critical for designing and optimizing almost everything about the mission. By simulating what Gaia would see, based on how it scanned the sky and how sensitive its detectors were, they could predict the sheer volume of data the satellite would encounter. How many stars per second, in which directions, how bright or faint.
And knowing the data fire hose was coming allowed them to design the hardware and software to handle it.
Exactly. That knowledge directly informed the technical specifications, things like how quickly the CCD detectors needed to read out beta, how much processing power and memory were needed on board the spacecraft, how much data needed to be beamed back to Earth per day, the downlink rate. It influenced a whole range of design choices for the scientific instruments.
Wow, so the BGM wasn't just some theoretical tool for later analysis. It actually helped shape the physical design of Gaia.
Absolutely. It played a direct role in making sure the mission was technically feasible. And beyond the hardware, it was also used extensively to develop and test the incredibly complex software pipelines that would later process the real Gaia data.
Ah, so.
Well, they could feed the simulated data from the BGM-based universe model into the processing software to test algorithms for, say, calculating precise star positions and motions, the astrometry. They used it to check how well the system could identify and handle binary stars, or match observations of the same star seen at different times. It helped build and debug the entire data processing chain.
That's incredible. It basically provided the test data to make sure the whole system would work once the real floodgates opened.
It really did. It laid a lot of the groundwork for Gaia's operational success.
So the BGM was vital for Gaia's design and preparation. Now let's shift to the present. Gaia has delivered these amazing datasets, DR1, DR2, EDR3. How is the BGM being used with all this real, high-precision information?
Right, this is where the interaction becomes really exciting. Each major Gaia data release has basically provided a much sharper lens to examine the galaxy, and in turn, to test and refine the BGM itself. This feedback loop has led to significant improvements in the model and, consequently, much deeper insights into the Milky Way.
Can you give an example of how the real data actually forced a change or refinement in the model?
Sure. Pretty early on, even using pre-Gaia data like the Tycho 2 catalog for bright stars, comparisons revealed some disagreements with BGM's predictions. It turned out the model was quite sensitive, especially in the thin disk component, to the assumptions made about certain types of stars, A and F-type dwarfs, and their formation history.
So the data showed the model's recipe for those stars wasn't quite right.
Essentially, yes. The mismatch highlighted areas where the model's assumptions needed improvement. This actually led to a more sophisticated strategy within the BGM for generating the thin disk population. Instead of just fixing parameters like the initial mass function or the star formation rate, they started treating them more like free parameters.
Free parameters,
Yeah.
meaning they could adjust them to better fit the observations.
Exactly. Letting the data guide the best values for those parameters. They also improved how binary stars were incorporated, making it more self-consistent. And this process, this cycle of compare and refine, allowed them to start putting actual constraints on things like the slope of the IMF for more massive stars.
Okay, so the model gets better by confronting the data. What happened when the big Gaia datasets, like DR2, arrived?
Well, DR2 was a huge leap in data volume and precision. That prompted a major revision of the BGM. The updated version incorporated more modern stellar evolution models, parsec tracks, specifically and explicitly included populations like white dwarfs, which are important end states of stellar evolution.
What else was new?
It also added components to represent the Magellanic Clouds, improved how open star clusters were modeled, even including their internal rotation, and crucially started using new detailed 3D maps of interstellar dust to better account for how dust blocks starlight in different directions. The model became much more physically detailed and realistic.
And then comparing that souped-up BGM to the next big release, Gaia EDR3, what kind of specific discoveries came out of that? This seems like where the payoff really happens.
It absolutely is. By comparing the refined model's predictions for stellar densities and motions to the billions of precise measurements in EDR3, scientists could start pinning down some really fundamental galactic properties. For example, looking at stars relatively close to the sun, they could refine estimates for the sun's exact height above or below the midplane of the galactic disk and nail down its motion relative to nearby stars, the solar motion.
Wait, hang on. The model helps figure out the sun's height in the galaxy. How does that work?
Well, the model predicts how stars should be distributed in density and how they should be moving, assuming a certain structure and the sun being at a certain position. By comparing that prediction to how the real stars observed by Gaia are distributed and moving, tiny systematic differences can reveal things like, oh, the sun is actually slightly above the midplane, or it's moving slightly faster in this direction than the average star nearby.
That's amazing. Deriving such precise local information from this global model and data. What else did the EDR3 comparison reveal?
One of the really big results involved using the BGM tuned to match Gaia's observed kinematics and densities to construct what's called the implied gravitational potential of the galaxy.
The implied gravitational potential.
Yeah.
Okay, what does that mean in plain English?
It basically means figuring out the overall distribution of mass, not just stars and gas we can see, but also the invisible dark matter by looking at how its gravity affects the way stars move and where they are located. They adjusted the BGM's parameters describing the stellar populations, particularly in the thin and thick disks, until the resulting motions and densities in the model matched what Gaia actually observed across large parts of the galaxy.
So you use the star's movements, as measured by Gaia, combined with a model, to map out the gravity field.
That's the essence of it, yeah. You're inferring the gravitational landscape based on how the stars are navigating it. And this analysis showed that the BGM, when adjusted this way, could reproduce the observed stellar densities and motions very consistently over a huge region, roughly from 6 up to 12 kiloparsecs out from the galactic center, and extending about 2 kiloparsecs above and below the galactic plane.
That covers a really significant chunk of the disk.
It does, and the analysis provided some fascinating details. For instance, it described the thin disk as being composed of roughly 7 distinct age groups, and each group has its own characteristic velocity ellipsoid.
Velocity ellipsoid. Sounds complicated.
It just describes the typical spread and orientation of velocities for stars in that group. Think of it like the shape of the swarm's movement. And they found that the shape and tilt of this ellipsoid change depending on the star's age, how far they are from the center, and how high they are above the disk plane.
So older stars move differently than younger stars, even in the same part of the disk.
In systematic ways, yes. The model helps quantify that complexity. Another finding was that the thin disk noticeably flares in the outer parts of the galaxy.
Flares. You mean it gets thicker?
Exactly, it puffs up vertically further out. The model showed this could be naturally explained by how the vertical pull of gravity changes as you move away from the galactic center. And importantly, the comparison revealed significant differences between, say, young stars belonging to the thick disk versus old stars in the thin disk, especially in how their average orbital speed around the galaxy changes with radius.
And the significance of those differences between thin and thick disk stars.
Well, these detailed distinctions in their structure, their kinematics, how they flare, it strongly supports the idea that the thin disk and the thick disk didn't form in the same way or at the same time. They likely have quite different origins and evolutionary histories.
Wow. So refining these models with Gaia data isn't just describing the galaxy now, it's helping us piece together its entire formation story.
It's putting really powerful constraints on how that story could have unfolded.
Yeah. That really shows the power of combining models and data. But, I mean, even with a sophisticated model like the BGM and amazing data from Gaia, it can't be perfect, right? Are there still areas where the model and the observations don't quite line up?
Oh, absolutely. And the researchers are usually quite upfront about that. The sources we looked at mention that while the overall fit is remarkably good, especially under that assumption of axisymmetry, noticeable discrepancies do pop up in certain specific regions or when looking at certain details.
Where do these mismatches tend to occur?
Well, one area is towards the galactic anticenter, looking directly away from the galactic core. Gaia has revealed a lot of complex substructure in the disk out there, things like stellar streams or ripples, that a smooth axisymmetric model doesn't fully capture.
Right, the real galaxy has lumps and bumps.
Exactly. Another area mentioned is looking towards the north galactic pole. Gaia data shows evidence of a sort of vertical wave pattern in the star positions there, possibly caused by something external like a past interaction, and the standard BGM doesn't inherently include that. And they also note that the model for the stellar halo component still needs refinement compared to the richness of detail Gaia sees there.
Okay, so these discrepancies aren't necessarily failures of the model, but more like signposts pointing towards where the galaxy's physics is more complicated than the current model assumes, or where the model itself needs new ingredients.
Precisely. They highlight the frontiers, the areas where our understanding is still incomplete, and where future modeling efforts need to focus.
And what about those other models you mentioned earlier, like TRILEGAL? Are people using Gaia data to test and improve those too?
Yes, definitely. The Gaia data is like a benchmark data set for the whole field. There's work cited, for example, using TRILEGAL with Gaia DR2 data, specifically looking at stars relatively nearby but high above the galactic plane.
And did they find anything interesting from that comparison?
They did. By focusing on improving how binary stars were handled in their model and optimizing parameters like the star formation rate and the binary fraction, they came up with some specific findings. For instance, they estimated that for lower mass stars, the fraction born in binary systems is around 40%, which is quite high, maybe twice as high as for more massive stars. They also derived a history for local star formation that peaked around 2 billion years ago.
Interesting. Specific numbers coming out of that comparison too. It's cool how different models, using the same incredible Gaia data, can provide these complementary insights.
Yeah, it shows the power of the data to constrain different theoretical approaches. Everyone benefits.
Okay, one last application mentioned in the sources that seems really important. Using models like the BGM to get better distance estimates for individual stars from Gaia. How does a model of the whole galaxy help figure out how far away one specific star is?
Oh, yes. This is a really crucial point, technically speaking. Gaia measures parallax extremely well, that tiny back and forth wobble of a star caused by Earth's orbit. And distance is basically inversely related to
Right,
parallax.
you usually hear distance is 1 divided by parallax.
And that simple formula works okay if the parallax measurement is super precise with a very small percentage error. But for a lot of stars, especially fainter or more distant ones, the uncertainty on the parallax measurement can be, say, 10%, 20%, maybe even more, relative to the parallax value itself.
Okay.
In those cases, just calculating 1 divided by the measured parallax gives you a distance estimate that's actually biased. It's systematically skewed and can be quite inaccurate.
So the measurement noise messes up the simple calculation.
Exactly. It introduces a mathematical bias. This is
Mm.
where galaxy models like the BGM come in. They provide what's called prior information.
Prior information, like background knowledge.
Precisely. It's our knowledge that stars aren't just randomly distributed in space. They live in structures, the disk, the halo, the bulge. They belong to populations that have typical densities and distributions of distances. The BGM encapsulates that statistical understanding.
So how does that help with the distance?
By incorporating this realistic galactic context from the model as a prior, you can essentially combine the noisy parallax measurement with the knowledge of where stars like this one are likely to be found in the galaxy. This statistical combination allows you to calculate a distance estimate that is much less biased and generally more accurate, especially for those stars where the parallax measurement itself has a large relative uncertainty.
Ah, I see. So the model provides a sort of reality check based on the galaxy's structure that helps you interpret the noisy parallax measurement more intelligently.
That's a great way to put it. It uses our global understanding of the galaxy to help us get a better handle on the distance to an individual star, effectively smoothing out the measurement noise by placing the star within its expected galactic neighborhood.
Okay, let's zoom out again then. We followed the Besançon Galaxy model on quite a journey. It started partly out of needing predictions for telescopes like Hubble. Then it became this incredibly vital tool for actually designing and simulating the Gaia mission. And now, in the Gaia era, it's being used as a key instrument to interpret Gaia's billions of measurements and refine our whole picture of the Milky Way.
Yeah, it's a fantastic example of the scientific process in action, isn't it? You build a model based on what you know, you get groundbreaking new data, you use that data to rigorously test and improve your model, and that whole cycle leads to deeper understanding, but it also clearly shows you where your model and your understanding still fall short.
It really does. And when you think about how these incredibly detailed models, sharpened by Gaia's data on billions of stars, can tell us things like the sun's precise position relative to the galactic plane, or help distinguish the formation paths of the thin and thick disks, or even let us infer the unseen gravitational scaffolding of the galaxy.
It's pretty mind-bending stuff.
It really is. It makes you wonder, what other fundamental secrets about the cosmos might be lying hidden within these enormous data sets, just waiting for the right model, the right way of looking to bring them out into the light?